Welcome. Good morning, everyone. I'm glad I can be here giving this talk to you. Thanks for coming. Today, I would like to share with you a debugging process of an Erlang application, Erlang system, along with tools that leverage one of the Erlang VM's coolest feature, which is Erlang tracing. And as a RabbitMQ is a piece of software that is powered by the Erlang virtual machine, I'm going to make use of it through the presentation to present the methodology and the tools. Before we begin, just a few words about myself. My name is Kacper Mentel. I'm a software engineer in Erlang Solutions. I've been working as a RabbitMQ consultant, and apart from that, I'm also involved in load testing and development of our open source XMPP server written in Erlang that is called Mongoose. Here you can see the agenda for today's presentation. I split the content into three main parts. The first one is called real-world problem. In this part, I would like to describe the problem that we had and how we reproduced that problem via load tests. And also, I will present the results of these load tests. The second part is about the actual debugging process. I will try to answer where to start questions, and also I will present tools I considered useful and applied during the debugging process. And in the last part, there will be a solution to the problem explained. So when working as RabbitMQ consultant, I saw different RabbitMQ installations with their different problems. And the problem I'm going to focus on today in this presentation is one of these. So one of our customers had a system that RabbitMQ was core of. As a side note, the version of used RabbitMQ in that system was 3.7.9. And in that system, among applications that interact with RabbitMQ, was an application that made some processing decisions based on queues data, like number of ready messages in each queue. That diagram depicts what the system looked like. So we have a RabbitMQ node with management plugin enabled. Management plugin is a component that allows you to manage RabbitMQ to some extent. It also gives you some insights into the system and allows to get some data, some statistics related to the RabbitMQ installation. It also exposes HTTP API that can be used to get some statistics about the system, like, for example, information about the queues. So the application was just periodically sending HTTP requests to the management plugin HTTP API to /API/queues endpoint to get data about the queues, and the plugin just returned that data to the application. But from time to time, it happened that obtaining the data from the API took a long time. Sometimes the application was even not able to get any response from the API at all. And as the application was not fed with the fresh data, it could not make optimal decisions. And because of that, the system became inefficient. And for our customer, that was a real problem. So to find a root cause of a problem, our plan looked as follows. So first, we wanted to reproduce the problem. Once we can do that, we could find a function, like Erlang function in the management plugin source code that handles HTTP requests that come to this management plugin HTTP API. And once we know exactly which function is responsible for that, we could learn how and where that function spends its execution time. So we ran load tests to reproduce the issue. For load tests, we used our continuous load testing platform that was developed for load testing Mongoose, this open source XMPP server that I have mentioned in the very beginning of the presentation. And the diagram shows a logical architecture of the platform. So what's worth remembering from that diagram is that we have 2 Docker hosts, one for system under test, which in our case was just a cluster of RabbitMQ nodes. The other Docker host is for load generators. The next thing is that every single application that is run in our load test platform runs inside a Docker container. When it comes to load generation, we use Amok, a murder of crows. This is a load generator that was created within Erlang solutions. It is written in Erlang, and it's open source. It was designed to support massively parallel load tests. When it comes to how Amok works, it's fairly simple. Amok has an abstraction that is called the user, which is just an Erlang process underneath, and the user follows certain scenario. The scenario is just an Erlang module, and because of that, we can simulate very complex behaviors because the only thing that is limiting us is just Erlang language itself. And the last thing is that system-level metrics, like, for example, CPU utilization of Docker containers, or some application-level metrics, like, for example, number of queues in RabbitMQ, or some custom metric that we implemented in an Amok scenario, are gathered and stored inside an influx database, so they can be later visualized, for example, using Grafana, so we can draw some conclusions on top of that later. We used the following load test scenario to reproduce the problem. The diagram shows a simplified version of the scenario. We just multiplied it in the final load test. So we have a queue, and that queue has 2 consumers that are marked with letter C and blue arrows. One producer that is marked with letter P here and red arrow. And there is also another Amok user with letter A and with green arrow. And it just simulates the application that was sending these HTTP requests to the management plugin HTTP API. And in the final load test, we sent an HTTP request every 2 seconds. When it comes to final load test specification, we had 3 RabbitMQ nodes, 3,000 queues, 3,000 publishers, 6,000 consumers, 20 connections that were shared between the MQP clients. Each node has 7 CPU cores available during a load test. 100% on that graph means 1 CPU core utilization. So each node consumed about 6 out of 7 CPU cores. So RabbitMQ was pretty busy in our load test. Memory consumption, second graph. So these 2 nodes consumed about 1.4 gigabytes of memory. The green one consumed a bit more. To be honest, I don't know why. I didn't investigate that. My guess is that this particular node maybe had to handle just more HTTP requests than the others. But anyway, nothing special here. There was plenty of memory available during the load test. And the last graph that shows response times to management plugin HTTP API requests to this /API/queues endpoint. This red line presents median, which was about 1.5 seconds. The other lines presents 95th, 99th, 999th percentiles and max values. So we can see that in peaks, they reach like about 20 seconds. And having these results, we considered our problem reproduction successful, or definitely things were slow. So the first point from our plan is checked. We reproduce the problem. Now we could try to find a function that actually handles these HTTP requests. So once we had our problem reproduced, we could start the actual debugging process. So the idea was to find an Erlang function that is called when a request to this /API/queues endpoint comes in, so we can later take a closer look at it. So where to start? First, we can manually look through the source code to find some candidates. I mean, to find functions that might be called when, in our case, a request to this management API endpoint comes in. And once we have some candidates, we can verify which one is the right one using Erlang tracing. And this is exactly what we did. And this management plugin uses Cowboy for serving HTTP requests. Cowboy is just an Erlang HTTP server, is well known in Erlang world. And in Cowboy, there is a mapping between HTTP endpoints and Erlang modules. So each endpoint has a dedicated callback module. And this toJSON function is one of the Cowboy's callbacks. And so this RabbitMQ toJSON function seemed to be the one that handled these HTTP requests. In the diagram, you can see the flow. So a request to /API/queues comes in. It is handled by Cowboy, which in turn calls toJSON callback, where the actual business logic resides. So in our case, it was just gathering data about the queues. But that was only a hypothesis that we had to confirm using, and we did that using Erlang tracing. So what is Erlang tracing? Tracing is a neat feature of the Beam that lets you inspect function calls, message passing directly on the VM real time as things happen. But what does it look like in practice? So in practice, you can attach an Erlang remote shell to a running Erlang node. You can enable tracing and provide a pattern that will match a particular function or functions. And when that function is called, there will be some information about that function call in the Erlang shell process mailbox, or if you use some higher level tracing library, like for example Recon, that information will be printed on the console. Let's move on to our example. So to confirm our hypothesis, we first attach an Erlang shell to running RabbitMQ node. Then we enable tracing for a toJSON function using Recon. As far as I know, Recon is shipped with RabbitMQ by default. So I used Recon instead of using tracing functions, Erlang tracing functions directly, because for me it has just easier API for simple tracing. And so we passed a tuple with module name, function name, and RET of that function that we would like to trace, and number of traces we would like to gather. And when we enter that function, as an output, we can see 1, which basically means that the pattern we provided matched one function in the system. And once we enable tracing, we just manually send an HTTP request to the management plugin HTTP API using curl. It's not visible on the snippet, but once we did that, the trace popped up. So as we can see, there are some information about that particular function call. There is a module name, function name, and arguments that were passed to that function call. So in this way, we confirm that we found the right function. So the second point from our plan is done. We know exactly which piece of code, which function is responsible for handling requests, these requests. So now we could start profiling that function. So one of the techniques that helps with profiling is using flame graphs. Flame graphs are a visualization of profiled software, allowing the most frequent code paths to be identified quickly and accurately. And it perfectly fitted our case, as we wanted to identify the most expensive code behind the API. So here you can see an exemplary flame graph. It shows a stack trace of a trace function. In other words, which functions are called from the trace one and how much resources they consume relatively to the trace one. Such visualization allows to quickly identify suspicious places in the code, as the longer bar the function has, the more resources it consumes. For example, dispatch command function on that graph calls some other functions from which the three visible on the left-hand side consume majority of its resources. For Erlang, we have iflame library that gathers traces of a particular function and builds a flame graph out of it. So we decided to use iflame in our load tests. But as I said before, every single application that is run in our load test platform runs inside a Docker container. So, and RabbitMQ was no exception. So there was a question: how could we inject that library into our Docker image? RabbitMQ Docker image. So we created a RabbitMQ Docker repository that makes it easy to build a RabbitMQ Docker image with modified or custom RabbitMQ source code. And we did a number of measurements, and this is what we've got: 2 different flame graphs. And these green rectangles highlight the most interesting parts of the graphs. And the main difference between these graphs is in run augmentation function. But what does the difference mean? From the load test results and manual code analysis, we knew that the query to management API sometimes works quickly, sometimes works slowly. In the load test results, the HTTP API response times median was about 1.5 seconds, while max values were about 20 seconds. And also, we manually measured execution time of that function, and that result were consistent with the others. And this happened because there is a cache in the management plugin, and when the cache is valid, the data about the queues are returned almost immediately. But when the cache is invalid, fresh data needs to be gathered, and that took time. Despite these 2 graphs have the same length, they represent different execution times. And the first one presents the case when the query works quickly, while the second one presents the case when the query works slowly. And in the second graph, you can see that the augment function takes so much time because the fresh data needs to be gathered. But the augment function is the second one below the, it's highlighted in this green rectangle, the smaller one. But why don't we see data collection function in these graphs? This is because that cache resides in another Erlang process. And this genserver call function, which is the second one below the blue bar with sleep, makes an actual call to the cache process and waits for a response. Depending on the cache state, the response can come back quickly or slowly. So here's a visualization of the interaction with the cache process. So fetch request is sent. When the cache is valid, cache data is returned to the original caller, but when the cache is not valid, fresh data needs to be gathered. That takes time, and then data about the queues is returned to the caller. This fetch request and queues data are sent via Erlang messages, because this is how Erlang processes communicate with each other. And collecting data is implemented in list queue stats function, which is invoked from the cache process. And we tried to profile that function with iflame, and after several dozens of minutes, this is what we've got. So Erlang heap memory allocator tried to allocate 42 gigabytes of memory and crash the server. As iflame takes advantage of Erlang tracing for generating flame graphs, it was simply overloaded with a number of trace events generated by the traced function. And that's where Fproof comes into play. Fproof, according to the official Erlang documentation, Fproof is a time profiling tool using trace to file for minimal performance impact. And indeed, the tool dealt with collecting data functions smoothly. However, it took several minutes to produce the results. And the output was quite big, so there are only crucial lines on the slides. And Fproof apply profiles a function and takes as arguments module name, function name, and its arguments. We profiled list queue stats function that's responsible for gathering data about the queues. That entry on the slide is the top level entry. The function marked with a % character is the one that the current entry concerns. The functions below are the ones that were called from the marked function. The third column, ACC, shows total execution time of a function expressed in milliseconds. So, for example, total execution time of pigrange function equals to 58 milliseconds. This particular entry concerns QStats function. And we can see that this function spent most of its execution time in format range function. And then we could go to an entry concerning that function and check where that function spent its execution time accordingly. And this way, we can go through the Fproof output and maybe find potential culprits of the management API slowness issue. Reading through Fproof output in a top-down fashion, we ended up with this entry. And this entry concerns exometer slide toNormalized list function, which in turn called two suspicious functions from the same module. And going deeper, we found this, ordict update and ordict find. And a lot of execution time was consumed by these two functions. They together used like 86% of total execution time. And this led us to exometer slide module from Rabbit Management Agent plugin. And if you check that module, you will find these functions and connections between them. So third point from our plan is checked. We know where that function spent its execution time. And we decided to close the investigation at this stage The issue is certainly there, no doubts. Maybe we'll share our thoughts with the community, so maybe we'll come up with some solid and reliable solution together. But all the presented investigation didn't happen while being at the customer side, but afterwards. So the solution to the problem that we applied for our customer approaches the problem from a slightly different angle. So let's think for a while if there is another way of obtaining queues names with corresponding number of messages in them. And it turned out that there is a RabbitMQ emidinfoAll function that allows to retrieve exactly that information that we were interested in, but directly from queues processes. So we could use that API from a custom RabbitMQ plugin and expose an HTTP endpoint that would return that information when queried. So we turned that idea into reality and built a proof of concept RabbitMQ plugin. This is called RabbitMQ QInfo that does exactly this. It just exposes an HTTP endpoint, which is called list queues. When a request to that endpoint comes in, information about the queues are gathered directly from queues processes and are returned to the original caller, to the calling entity. The plugin was load tested. The specification was exactly the same as the one for management HTTP API load test. And here are the results. The first graph is the one that I have already shown you. It shows management HTTP API response times. And the second graph shows response times to HTTP queries, HTTP requests to this list queues endpoint from this RabbitMQ QInfo plugin. You can see that the median is below 200 milliseconds, while percentiles and max values are slightly higher, but in majority of cases still below 300 milliseconds. So the performance of the second plugin, RabbitMQ QInfo, was definitely better. Is definitely better than the management plugin HTTP API. And yeah, that's basically it. At the end, I would like to say thank you to my brother, Kacper Mentel, who helped me a lot with all of this investigation and all the stuff. And also a big thank you to Andrzej Telezinski, who also helped me a lot with this stuff. He was actually involved in the whole process of debugging and developing that plugin. And also thank you to all of you for your attention and for being here. Thank you.
Okay, thank you very much, Kacper. It's an opportunity for the audience to ask a couple of questions. Do we have any questions at all? John.
Just quickly, how did you choose the load test parameters? Were they just what the client was, was it their base load, or was there some insight that you used to generate that?
As far as I remember, because it happened some time ago, we just experiment. We just empirically do some load tests, and we were monitoring the results. So once we got to the point when we can see that the management plugin, that the response of the management plugin HTTPI were slow, then we know that the problem is reproduced.
Thanks.
Thank you for the talk. It was great. I have one question. Is there a PR here that you could submit to maybe RabbitMQ management?
No, there is not.
Why?
Actually, there wasn't like an obvious solution, and also there wasn't a pressure to fix this. I tried to replace ordicts with GB trees, but with no success.
So I'm wondering along the lines of maybe introducing a new API endpoint that would do what you wanted to do. Sorry.
We kind of have one similar endpoint that we list only the queues. I don't remember which parameters we do. We do the info that we introduce it to have a small management plugin to work with Prometheus. So you only do management and not a stat. But you still need to list the queues. And it uses the info all. I don't remember from the top of my head which parameters we use. But it's there, and well, it was a very simple change. So if we don't provide all the parameters, that could be easily extended, and that PR shouldn't take more than a few hours, in fact.
Thank you very much. I have a quick question.
Yeah.
Do you need to be an Erlang engineer to debug Rabbit?
I think if you would like to go deeply into the source code, of course, you have to know Erlang, like to understand what's there. But for simple stuff, I think definitely no. You don't have to be an Erlang engineer to attach Erlang shell to RabbitMQ and type some recon comments. Maybe, if not tracing, you can also use recon to, for example, check processes mailbox length, or for example, to analyze memory somehow to see what's there. So the answer, from my perspective, is no. You don't have to be an Erlang engineer to start debugging.
So, sorry. So I've been using Fproof once and spent some nice hours wading through the output. Any tips or insight, or maybe even tooling that can be used here?
To be honest, I don't know. In our case, I also had to wait, but it was like several minutes to get the output. So to be honest, I don't know.
Okay, I didn't find them super easy to read, to be honest.
There's one thing which I can mention. There's one thing which I can mention in the RabbitMQ GitHub repo. There's, in the RabbitMQ GitHub org, there's Looking Glass, which is meant to facilitate tracing of high volume data, and it was built for high volume data. So you mentioned waiting a couple of hours.
No, the waiting through the Fproof output.
Right.
Several hours.
Right.
Okay.
So Looking Glass, when it captures things, it can also output to build your flame graphs, and it's fast because it was optimized for similar scenarios. We couldn't understand what was happening because of the scale, so this was making it easier. So Looking Glass, check it out.
Okay, cool, thanks.
Okay, thank you very much. Kacper, please give him a round of applause.